Mars is closer to Earth than any planet with a solid surface you could stand on. It has a 24-and-a-half-hour day. It has polar ice caps. It has seasons. It has canyons deeper than the Grand Canyon and a volcano taller than anything we have got. And if you listen to enough excited talk, you come away with the impression that the only thing standing between humanity and a nice little colony on Mars is a better rocket and some clever engineering. Build the habitat, ship the food, pressurize the dome. Done. Move-in day. And I want you to sit with that idea for a moment because it sounds so reasonable. It sounds like the same kind of problem as building a submarine or a space station or a research base in Antarctica. Hard engineering, big budgets, but ultimately solvable. We put men on the moon, after all. Surely Mars is just a longer trip with a bigger lunchbox. Well, that is completely wrong. And I can show you why, using nothing fancier than basic physics. See, the trouble with Mars is not that it is far away. The trouble is not that the trip takes a long time, although it does. The trouble is that Mars is trying to kill you in about 6 different ways at once, and most of those ways are not engineering problems. They are physics problems, and physics problems do not care how much money you throw at them. Physics problems do not negotiate. They just sit there being true, whether you like it or not. So let me walk you through what Mars actually is, physically, and why the cheerful diagrams of little greenhouses on the Martian surface are leaving out some rather important details. Let us start with the most basic thing. Air. You need air. On Earth, you walk around in a nice thick blanket of atmosphere pressing down on you at about 101,000 pascals. That is what we call 1 atmosphere of pressure. Your body is built for it. Your lungs are built for it. Every blood vessel, every cell membrane, every fluid balance in your body is calibrated to operate inside that pressure. Mars has an atmosphere. People always mention that. Mars has got an atmosphere, great, except the average surface pressure on Mars is about 600 pascals. 600, that is less than 1% of what you are breathing right now. To get the equivalent pressure on Earth, you would need to go up to about 45 kilometers above the surface. That is not the top of a mountain. That is higher than any airplane flies. That is the edge of space. That is the kind of altitude where even the Air Force starts worrying about their pilots. And it gets worse. There is a number in aerospace medicine called the Armstrong limit, named after Harry George Armstrong, an Air Force flight surgeon who figured this out back in the 1930s and 40s. The Armstrong limit is the altitude at which the atmospheric pressure drops low enough that water boils at the normal temperature of the human body, 37 degrees Celsius. On Earth, that altitude is about 19 kilometers up, above the Armstrong limit. Exposed body fluids, your saliva, your tears, the thin film of moisture lining the inside of your lungs, they begin to boil, not because they are hot, because the pressure around them is too low to keep them liquid. The pressure at the Armstrong limit is about 6.3 kilopascals, 6,300 pascals. The surface pressure on Mars is 600 pascals. You see the problem? Mars is not just below the Armstrong limit. Mars is 10 times below the Armstrong limit. If you stepped outside on Mars without a pressure suit, the moisture on your tongue would begin to boil instantly. Your eyes would swell, the fluid lining your lungs would vaporize. You would not suffocate. Exactly, something more violent than that would happen first. The medical term is ebulism. Gas bubbles forming in your tissues, your body inflating like a grotesque balloon. You would lose consciousness in maybe 15 seconds. You would be dead in a few minutes. Now, I should mention something about the composition of that atmosphere, because even if you could somehow pressurize it enough to breathe, you would still be in deep trouble. The Martian atmosphere is 95% carbon dioxide, about 3% nitrogen, a bit of argon, and oxygen, 0.13%. That is essentially zero. On Earth, you breathe air that is about 21% oxygen. Your body needs a partial pressure of oxygen of at least about 16 kilopascals to function normally. On Mars, even if the total pressure were magically raised to Earth levels, the oxygen partial pressure would still be far too low to sustain you. And the carbon dioxide, at those concentrations, it is actively toxic. Carbon dioxide is not just air. You cannot breathe. It is a poison. At concentrations above about 5%, it causes headaches, confusion, rapid breathing. Above about 10%, unconsciousness and death. 95% carbon dioxide would kill you faster than the lack of oxygen would. So the Martian atmosphere attacks you from 3 directions at once. Too thin to keep your body pressurized. Too little oxygen to sustain your metabolism. Too much carbon dioxide to avoid poisoning your blood. And we have not even mentioned the ultraviolet radiation pouring through that thin atmosphere, unfiltered by any ozone layer, sterilizing the surface like a hospital lamp. Mars has no ozone layer because there is virtually no free oxygen to form ozone from. The raw ultraviolet light from the sun hits the ground unimpeded. If you laid a petri dish of bacteria on Martian soil in direct sunlight, they would be dead within minutes. So no, you cannot step outside for a breath of fresh Martian air. That was probably obvious. But let me point out what is less obvious. On Earth, the failure of a window, a crack in a wall, a leaky seal on a door, these are nuisances. On Mars, any breach in your habitat is not a leak. It is an explosion. The pressure difference between inside and outside is nearly a full atmosphere. Every wall, every window, every airlock is a pressure vessel. Your entire living space is a balloon inflated to 14.5 pounds per square inch against an outside world that might as well be a vacuum. Now think about that for a moment in terms of engineering reliability. Every seal, every joint, every weld, every hatch must hold that pressure difference. Not for a week, not for a month, for years, for decades. If you are talking about a colony, and any failure anywhere is catastrophic. On a submarine, if you spring a leak, water comes in slowly. You have time. On Mars, if you spring a leak, air goes out fast. The atmosphere screams out of any opening because the pressure gradient is so enormous. You might have seconds to react depending on the size of the breach. This is not an unsolvable engineering problem. We build pressure vessels all the time, but it changes the nature of the challenge fundamentally. You are not building a house on Mars. You are building a spacecraft that never moves. And every spacecraft we have ever built requires constant maintenance, constant monitoring, and has a limited operational lifetime. Nobody lives permanently on the International Space Station. Crews rotate, equipment gets replaced, whole modules eventually fail and have to be abandoned. And here is another thing about pressure vessels that people forget. Fatigue. Materials under constant stress develop fatigue over time. Metals crack, seals degrade, polymers become brittle. On Earth, a building can stand for centuries because the structural loads are modest relative to the strength of the materials. On Mars, your habitat walls are under constant tension, holding back nearly a full atmosphere of pressure difference. Every thermal cycle, every day-night temperature swing, every vibration from equipment contributes to material fatigue. Mars has temperature swings of 80 to 100 degrees Celsius between day and night at some latitudes. That means your structure is expanding and contracting day after day, year after year. Every expansion and contraction stresses every joint, every seal, every weld. On Earth, thermal cycling is a well-known source of structural failure in bridges, pipelines, and aircraft. We manage it through inspections, maintenance schedules, and eventual replacement. On Mars, who inspects, who replaces, with what spare materials, made from what manufacturing base? And consider this, the atmosphere on Mars, thin as it is not gentle. Mars has dust storms, not little dust devils, although it has those too. Mars has global dust storms that can engulf the entire planet for months at a time. These storms carry fine abrasive particles at speeds that, while not hurricane force due to the thin air, are persistent and relentless. This dust coats everything. It infiltrates every crevice. It abrades surfaces. It clogs filters. It degrades solar panels. And over years and decades, it would grind away at any exterior surface of your habitat. Seals that were airtight on day one might not be airtight after a decade of dust abrasion and thermal cycling. Now let me take you to the second problem. And this one is sneakier. Radiation. On Earth, you are shielded from the worst of cosmic radiation by two things. The first is our magnetic field. Earth has a molten, churning core of iron and nickel that generates a powerful magnetic field, extending tens of thousands of kilometers into space. This magnetosphere deflects charged particles, galactic cosmic rays, solar wind, the high-energy protons, and heavy nuclei that come screaming in from every direction. The magnetic field sweeps most of them around the planet. You never even notice. The second shield is the atmosphere itself. Even the particles that make it past the magnetic field still have to plow through a thick column of air. The atmosphere absorbs and scatters a tremendous amount of incoming radiation before it ever reaches the surface. Mars has neither of these protections. Mars lost its global magnetic field somewhere around 4 billion years ago. The planet's core cooled, the churning stopped, the dynamo switched off. And once that happened, the consequences cascaded. Without the magnetic field, the solar wind had direct access to the upper atmosphere. Over hundreds of millions of years, it stripped away molecule after molecule. The atmosphere got thinner. As the atmosphere thinned, the surface pressure dropped. As the pressure dropped, liquid water could no longer exist on the surface. It either froze or evaporated and was carried away by the solar wind. Rivers dried up, lakes vanished. Whatever Mars once was, it died slowly because the engine in its core went cold. Recent simulations have shown something even more surprising. A weak magnetic field, the kind Mars had for a while after its dynamo was fading, might actually accelerate atmospheric loss compared to having no field at all. The weak field lines get pushed back by the solar wind, creating channels that funnel atmospheric ions out into space faster than they would escape without any field. So Mars did not just lose its shield. For a while, the remnants of its shield may have made things worse. Physics can be cruel that way. Today, Mars has only faint remnant magnetic patches in its crust, the fossil imprints of the field that once was. These patches are too weak and too localized to provide meaningful shielding against either cosmic rays or solar wind stripping. And the atmosphere. We already discussed how thin it is. 600 pascals. That column of mostly carbon dioxide stops maybe 1 or 2% of incoming cosmic radiation, compared to Earth's atmosphere, which is like standing behind a wall of lead. The Martian atmosphere is like holding up a sheet of tissue paper against a fire hose. So what hits the Martian surface? Two things, mainly. First, galactic cosmic rays. These are not coming from the sun. They come from everywhere else. Supernova remnants, active galactic nuclei, sources scattered across the galaxy and beyond. They are mostly protons, about 85%, plus some alpha particles, and about 1% heavy nuclei. But that 1% of heavy nuclei is where the real trouble lives. These are atoms, iron atoms, carbon atoms, oxygen atoms, stripped of their electrons and accelerated to enormous energies. Some of them are traveling at a significant fraction of the speed of light. When one of these heavy ions hits living tissue, it does not just ionize a molecule or two, it plows a track of destruction through your cells like a microscopic cannonball. It breaks DNA strands, it shatters chromosomes, and unlike a dental X-ray where the energy is low and the damage is mostly repairable, these heavy ion impacts cause complex clustered damage that your body's repair mechanisms struggle with. The second threat is solar particle events. The sun periodically belches enormous clouds of energized protons, usually associated with solar flares or coronal mass ejections. Most of these particles are lower in energy than galactic cosmic rays, but they come in overwhelming numbers. A big solar event can deliver a huge dose of radiation in a matter of hours. On Earth, the magnetic field deflects these events beautifully. On Mars, you just get hit. A physicist at the European Space Agency calculated that 1 day in deep space exposes you to about the same radiation dose that a person on Earth receives in an entire year. On the Martian surface, with the thin atmosphere providing a modest reduction, the dose is somewhat lower than in open space, but still enormously higher than on Earth. Estimates from instruments on NASA's Curiosity rover suggest that an astronaut on Mars would accumulate roughly 2/3 of a millisievert per day. Over the course of a year, that is about 240 millisieverts. The average person on Earth gets about 6 millisieverts per year from natural background radiation. So on Mars, you are soaking up roughly 40 times the natural radiation dose every year. And here's the subtle part that makes this worse than it sounds. Galactic cosmic rays cannot be shielded against in any practical way. This is a critical point. With solar particle events, you can duck behind something dense. Water works, regolith works. A few meters of packed Martian soil would stop most solar protons. But galactic cosmic rays, the high-energy heavy nuclei, when these hit shielding material, they do not just stop. They shatter. They undergo nuclear fragmentation, producing showers of secondary particles, neutrons, lighter ions, gamma rays that can be even more biologically damaging than the original particle. NASA ran the numbers on aluminum shielding, the kind used in spacecraft. Adding more aluminum actually makes the radiation dose worse beyond a certain thickness, because you generate more secondary particles than you block primary ones. The only material that helps significantly is hydrogen-rich shielding, water, polyethylene, things like that. But you need a lot of it, several meters of water equivalent. That is an enormous amount of mass to put between you and the sky, especially when you need to protect an entire habitat, not just a closet. So the radiation situation on Mars is not bad but manageable. It is an open research problem. NASA's own radiation experts have said, and I am paraphrasing here, that with current shielding technology, a Mars mission would exceed acceptable career dose limits for astronauts. We are not talking about a small overage. We are talking about a fundamental conflict between the physics of cosmic ray interaction and the biology of human cells. Studies on animals exposed to simulated galactic cosmic rays showed persistent cognitive impairment, with memory problems, difficulty with decision-making, increased anxiety, reduced rates of fear extinction, which means the brain becomes less able to let go of fear responses. The damage was still measurable 6 months after exposure, and this was from doses comparable to what a Mars mission would deliver. The researchers found that the radiation caused measurable reductions in the complexity and density of the branching structures, called dendritic spines, on neurons in the prefrontal cortex. That is the part of the brain you use for planning, judgment, and problem-solving. Exactly the faculties you need most when you are 8 months from the nearest hospital, and everything you do is a matter of life and death. Imagine that. The very environment you are living in is slowly degrading the one organ you absolutely cannot afford to lose function in. That is not an engineering problem with a wrench-and-weld solution. That is a physics problem fighting a biology problem, and currently biology is losing, and I have not even mentioned the dirt yet. The soil of Mars is toxic. This is one of those things that catches people off guard, because soil sounds so benign. Dirt, ground. What could be dangerous about dirt? But Martian regolith, which is the technical name for the surface material, is laced with perchlorate compounds. The Viking landers discovered this back in 1976, and the Phoenix lander confirmed it in 2008. Perchlorates are salts of perchloric acid, and they are extremely reactive oxidizing agents. On Earth, perchlorate contamination in water is a regulated health hazard even at parts per billion. In the Martian soil, concentrations are measured in parts per million, much higher. If you ingest perchlorate, it interferes with your thyroid gland's ability to absorb iodine, which in turn disrupts the production of thyroid hormones. Thyroid hormones regulate your metabolism, your growth, your brain development. Chronic perchlorate exposure can cause hypothyroidism. In children, it can impair cognitive development. And on Mars, this stuff is everywhere. It is in the soil. It will be in the dust. And Martian dust gets into everything. Martian dust is extraordinarily fine, finer than talcum powder. The particles are on the order of a few micrometers. And because Mars has dust storms, big ones that can engulf the entire planet for months, this dust is airborne constantly. Any habitat will have dust infiltration. Any airlock will let some dust in. Spacesuits will be covered in it. And the dust is not just perchlorate laden. It also contains iron oxides that give Mars its red color. And these fine particles are potentially damaging to lungs in the same way that asbestos or silica dust is dangerous on Earth. Fine particle inhalation causes inflammation, fibrosis, and over time irreversible lung damage. So the very ground you are standing on, the dirt you might want to grow food in, is poisoned. And the dust from that ground is trying to get into your lungs and your equipment at every opportunity. Any agricultural effort on Mars would need to not only pressurize and heat and light the growing environment, but also somehow wash or process the soil to remove perchlorates before plants could safely grow in it. Or you grow everything hydroponically in purified water using processed nutrients, which brings us right back to the energy question. Let me shift gears now and talk about something that sounds more hopeful at first. Gravity. Mars has gravity, about 38% of Earth's, so you are not floating around. You can walk. Things fall when you drop them. It feels like something. But here is the question nobody can answer yet with any confidence. Is 38% enough? We know what zero gravity does to the human body. We have decades of data from space stations. In microgravity, astronauts lose bone density at a rate of about 1 to 2% per month in their weight-bearing bones. Their muscles atrophy. They lose muscle mass at a rate of up to 20% in the first month if they do not exercise vigorously. Their cardiovascular system deconditions. Their hearts shrink slightly. Their blood pressure regulation goes haywire. They develop vision problems from increased intracranial pressure. Their immune systems weaken. The space station astronauts exercise for 2 hours a day to slow these effects, 2 full hours of resistance training and cardiovascular exercise every single day, and they still come back to Earth, noticeably weakened. After 6 months on the station, some astronauts need to be carried out of their capsules. Recovery takes weeks to months. Some bone density loss may never fully reverse. That is in zero gravity with an aggressive exercise program. On Mars, gravity is 38% of Earth's, which is better than zero, certainly. But is it enough to maintain human health indefinitely? Nobody knows. We have never studied the long-term effects of partial gravity on humans. Not lunar gravity, not Martian gravity, nothing between 0 and 1. We went to the moon, sure, but the longest anyone stayed was about 3 days. That tells us nothing about what a year or 5 years or a lifetime at 38% gravity would do. Indirect evidence is not encouraging. A systematic review of what we know about partial gravity suggested that gravity levels below about 40% of Earth's are probably insufficient to maintain full musculoskeletal and cardiopulmonary conditioning over the long term. Mars sits right at that boundary, perhaps below it. And the review noted that adequate countermeasures, meaning exercise programs that could compensate, appear to be unavailable with current technology. Think about what that means for a so-called colony. You are going to raise children on Mars, children whose bones develop in 38% gravity, children who may never be able to visit Earth because their skeletal system never developed the density to handle 3 times the gravitational load they grew up in. Nobody has studied fetal development in partial gravity. Nobody has studied childhood growth in partial gravity. Nobody has any idea what happens to a developing human brain, a developing cardiovascular system, a developing skeleton, in an environment where everything weighs a third of what it should. This is not pessimism. This is just honest accounting of what we do not know. And what we do not know is enormous. Now I want to talk about something people rarely mention when they get excited about Mars. Energy. Everything on Mars requires energy. Heating your habitat requires energy because the average surface temperature is around minus 63 degrees Celsius. That is minus 81 Fahrenheit. In winter, at the poles, it can drop to minus 140 degrees Celsius, cold enough that the carbon dioxide in the atmosphere freezes out as dry ice, snow. You must heat your habitat continuously or everyone dies. Producing breathable air requires energy. The atmosphere is 95% carbon dioxide with only trace oxygen. You need to crack carbon dioxide molecules apart to get oxygen, or you need to electrolyze water, or you need to run biological life support systems with plants. All of these demand significant continuous power. Producing water requires energy. There is water ice under the Martian surface, yes, particularly at higher latitudes. But it is mixed with soil. It needs to be excavated, heated, melted, purified. Continuous energy. Growing food requires energy. Mars gets about 43% of the sunlight that Earth gets because it is farther from the sun. So your greenhouse needs supplemental lighting, or your growing season is long and your yields are low. Plants also need warmth, pressurized atmosphere, and carefully managed nutrients. All energy intensive. Maintaining pressure in your habitat requires energy. Your air recycling system, your carbon dioxide scrubbers, your humidity control, your temperature regulation. All energy all the time. And running all of this equipment means you need to manufacture replacement parts or bring them from Earth. Manufacturing on Mars requires energy. Smelting ore requires energy. 3D printing requires energy. Everything loops back to the same question. Where does the power come from? Solar panels work on Mars, but they produce less than half the power per square meter that they produce on Earth, because Mars is farther from the sun. And Martian dust storms can blanket the planet for weeks or months, reducing sunlight to a fraction of normal. Remember Opportunity, the Mars rover? It survived for 15 years, far beyond its planned 90-day mission, until a planet-wide dust storm in 2018 blocked so much sunlight that its solar panels could not keep it alive. Nuclear power is the other option. Small fission reactors could provide reliable, continuous power regardless of dust storms. But nuclear reactors require careful shielding. They require maintenance. They require trained operators. And they have limited fuel. You would need to either bring fissile material from Earth or figure out how to mine and refine uranium on Mars, which would require an entire industrial infrastructure that does not exist. And there is a subtlety about power on Mars that people overlook. On Earth, if your power plant breaks down, you call a repair crew. On Mars, your repair crew is the same 6 or 8 people who are also the doctors, the farmers, the geologists, the engineers, the plumbers, and the cooks. Every human in a Mars habitat is a critical system. If one person gets sick, the entire operation is degraded. There is no workforce to draw from. There are no specialists on call. Every person does multiple jobs, and they do them in an environment that is physically exhausting, psychologically isolating, and as we discussed, potentially brain-damaging from radiation. This brings up something that is technically not physics, but is closely related. Human psychology in extreme isolation. Soviet and Russian cosmonauts, who spent a year or more on Mir and the International Space Station, reported significant psychological effects. Depression, irritability, sleep disruption, interpersonal conflicts that became explosive in confined quarters. And those cosmonauts could look out the window and see Earth. They could talk to their families in real time or close to it. They knew that rescue was possible, that they could come home. On Mars, you are so far from Earth that home becomes an abstraction. The time delay in communication means you cannot have a normal conversation with anyone back on Earth. A question takes at minimum 6 minutes to get a reply. At maximum 44 minutes. Try having an emotional conversation with those pauses. Try getting counseling with a 20-minute gap between sentences. The psychological pressure of knowing that you are utterly, fundamentally alone with no possibility of quick return, with no rescue if things go wrong, is something no human has ever endured for more than a few days, and those were the Apollo missions to the moon, where Earth was only 3 days away. A Mars crew would be isolated for a minimum of 2.5 to 3 years. Some proposals talk about one-way trips, about people who go and never come back. Think about the psychology of that decision, not just for the people who go, but for the small community they would form, a community of perhaps a dozen people trapped together in a space the size of a few apartments, knowing that this is it. This is all there will ever be for the rest of their lives. Human beings are social animals who evolved in groups of a few hundred in open landscapes with the ability to walk away from conflict. On Mars, you cannot walk away, you cannot take a break, you cannot visit a friend in another town. The walls of your habitat are the borders of your entire world. The energy budget for keeping humans alive on Mars is not like the energy budget for keeping humans alive in Antarctica. In Antarctica, the air is breathable, the pressure is normal. There is abundant water in the form of ice that you just melt. You do not need to manufacture your atmosphere. On Mars, you have to manufacture everything. Every breath, every glass of water, every bite of food, every degree of warmth, and any interruption in that power supply is not an inconvenience. It is a death sentence. Now let me back up and talk about the journey itself, because the trip to Mars has its own physics problems that people gloss over. Earth and Mars are not always the same distance apart. At their closest approach during what is called opposition, they are about 55 million kilometers apart. At their farthest, they are over 400 million kilometers apart. You can only launch efficiently to Mars during transfer windows that open roughly every 26 months when the orbital geometry works out. Using the most fuel-efficient trajectory, what is called a Hohmann transfer orbit, the trip takes about 7 to 9 months each way. That is 7 to 9 months in a spacecraft, in microgravity or near microgravity, soaking in cosmic radiation, with no possibility of rescue or resupply. If something goes wrong 3 months into the trip, you cannot turn around. Orbital mechanics does not work that way. You are committed. The most energy-efficient abort option might still take months. You are farther from medical help than any human being has ever been. And communication. The speed of light is finite. It takes between 3 and 22 minutes for a radio signal to travel between Earth and Mars depending on their relative positions. That is one way. A round-trip message takes 6 to 44 minutes. You cannot have a real-time conversation. If a medical emergency happens on Mars, you cannot call a doctor and get advice in time. You have to handle it yourself, with whatever you brought. This means that a Mars crew must be entirely self-sufficient in terms of medical capability. Every surgery, every diagnosis, every emergency treatment, but also self-sufficient in terms of hardware repair, software debugging, psychological support, conflict resolution. There is no going home if things get bad. There is no supply ship arriving next month. The next launch window is over 2 years away. Speaking of getting there, there is a fundamental equation in rocketry that constrains everything we do in space. It is called the Tsiolkovsky rocket equation, and it is beautifully simple and utterly merciless. It says that the change in velocity you can achieve depends on the exhaust velocity of your rocket and the natural logarithm of the ratio between your initial mass and your final mass. That ratio is called the mass ratio, and the logarithm is what makes it brutal. If you want to go faster or carry more payload, you need more fuel. But more fuel means more mass, and more mass means you need more fuel to accelerate that mass. And that additional fuel adds more mass. You see the spiral. This is sometimes called the tyranny of the rocket equation, and it means that for every kilogram of cargo you want to deliver to the surface of Mars, you need many, many kilograms of fuel back at launch. The exact ratio depends on your propulsion system, but with current chemical rockets, it is devastating. Getting a single kilogram to the Martian surface costs something in the range of tens of thousands of dollars, and that is an optimistic estimate. Let me make that concrete. A human being needs at a bare minimum about 2,000 calories of food per day. A kilogram of dry food provides maybe 3,000 to 4,000 calories. So one person needs roughly half a kilogram of food per day, at minimum. That is about 180 kilograms per year. For 10 people, 1,800 kilograms of food per year. And that is just the food. You also need water, which can be partially recycled but not perfectly. You need spare parts, filters, medical supplies, clothing, tools, seeds, chemicals, electronics. A realistic estimate for the total consumables required per person per year on Mars, assuming substantial recycling, is somewhere around 1,000 to 2,000 kilograms. For 10 people over 2 years between resupply windows, that is 20 to 40,000 kilograms of consumables. And at current launch costs, delivering that mass to the Martian surface would cost somewhere in the range of hundreds of millions to billions of dollars. Per resupply, every 26 months. So when someone casually says we will ship supplies, remember that every kilogram of food, every spare part, every medical supply, every tool, every liter of water is obscenely expensive to deliver. A self-sustaining colony requires either complete self-sufficiency, manufacturing everything locally, or a continuous supply chain of staggering cost, and complete self-sufficiency requires an industrial base, mining, refining, manufacturing, that would itself require enormous amounts of equipment to bootstrap, equipment that must also be shipped from Earth at those same staggering costs. Now let me pull all of this together, because I have been poking holes in the cheerful picture for a while, and I want to be fair about what I am actually saying. I am not saying humans cannot go to Mars. We probably can. The physics allows a visit, a short-duration mission, perhaps on the surface for a year or two, with very careful planning, aggressive radiation shielding, extensive life support, and an enormous logistical tail stretching all the way back to Earth that is probably achievable within the bounds of what we know. What I am saying is that living on Mars in the way we live on Earth is something entirely different. The word colony implies permanence. It implies self-sufficiency. It implies generations. And the physics of Mars creates barriers to permanence that are qualitatively different from any engineering challenge we have ever faced. On Earth, if your technology fails, nature provides a fallback. The air is breathable. The water is drinkable, mostly. But the pressure is right. The temperature is survivable in most places, most of the time. But the radiation is low. Gravity is correct. You can walk outside and live. That is what a habitable planet means. It means the physics of the environment is compatible with the physics of your body. Mars is not habitable. Let me be very precise about that. Mars is not habitable. It can be visited. It can perhaps be occupied the way we occupy a submarine or a space station, in an engineered bubble that must be maintained at all times. But the planet itself is actively hostile to human biology in multiple independent ways, simultaneously. The pressure will kill you in seconds. The temperature will kill you in minutes. The atmosphere will poison you. The radiation will damage your cells continuously at rates that may cause cancer, may cause brain damage, may cause heart disease, and will certainly accumulate over a lifetime. The gravity may slowly degrade your body in ways we cannot yet quantify, and every single one of these threats requires continuous uninterrupted technological intervention to survive. I want you to really think about what continuous uninterrupted technological intervention means over a timescale of generations. Every power plant must keep running. Every air system must keep recycling. Every seal must hold. Every piece of critical equipment must either last forever or be replaceable locally. There is no margin. On Earth, civilizations have risen and fallen, empires have collapsed, dark ages have come and gone, and through all of it, people survive because the planet itself is livable. On Mars, if your civilization falters, if your power grid goes down, if your knowledge is lost, if your supply chain breaks, everyone dies. Not in years, in days. That is a different kind of fragility than anything our species has ever experienced. We have always had the Earth beneath us as a safety net. Mars offers no safety net. Mars offers physics. Now, here is where I want to turn from what sounds like a warning into something more interesting. Because understanding why Mars is so hostile actually teaches you something wonderful about Earth. Every single protection that Mars lacks, Earth provides. And Earth provides these protections not through any engineering, not through any conscious design, but through the sheer beauty of physics operating at planetary scale. Our magnetic field exists because our planet is large enough and still hot enough inside that molten iron circulates in the outer core, generating electric currents that produce a magnetic dipole field. This has been going on for billions of years. It is a self-sustaining dynamo powered by the slow cooling of the planet and the crystallization of the inner core. It is, when you think about it, one of the most remarkable physical systems in nature. A planet-sized electromagnet running itself, shielding an entire biosphere from particle radiation. Our atmosphere is thick because our gravity is strong enough to hold on to heavy molecules, and because our magnetic field prevented the solar wind from stripping the atmosphere away over geological time. Mars, being smaller, with weaker gravity and no magnetic field, lost the battle. Its atmosphere was slowly peeled away, molecule by molecule, over billions of years. What remains is a ghost of what was once there, and with the atmosphere went the surface water, evaporated, and lost to space. Our ozone layer exists because there is enough oxygen in our atmosphere, produced by photosynthetic life over billions of years, to form a stable layer of ozone in the stratosphere. This thin layer absorbs the worst of the sun's ultraviolet radiation. Mars has no ozone layer. The ultraviolet light reaching the Martian surface is intense enough to sterilize exposed organic material within minutes. The temperature of Earth is regulated by a complex interplay of greenhouse gases, ocean currents, albedo, and biological processes that have co-evolved over the entire history of the planet. This is not a thermostat you can build. This is a system of staggering complexity operating across the entire surface of a world. So when someone looks at Mars and says, "We will build a greenhouse, we will make some oxygen, we will make it work," they are proposing to replace with small machines in a small habitat what Earth accomplishes with a molten iron core 5,400 kilometers across, an atmosphere weighing 5 quadrillion metric tons, a magnetic field extending 65,000 kilometers into space, an ozone layer maintained by the metabolic output of billions of organisms, and a biosphere that has been self-regulating for nearly 4 billion years. That is what you are replacing, the entire planetary infrastructure of habitability. I do not say this to mock ambition. Ambition is fine. Ambition is necessary. But ambition without physics is fantasy. And I would rather we were honest about what the physics says, so that when we do go to Mars, and I believe we will, we go with our eyes open. We go understanding that we are not homesteading, we are doing something more like deep-sea diving. We are visiting an environment that is not ours, that will never be ours in any comfortable sense, and that requires constant, vigilant, unforgiving technological support to survive in. There is a habit in the way people talk about science and exploration that bothers me. They talk about conquering nature. We conquered the sky. We conquered the ocean. We will conquer Mars. But you do not conquer physics. You cannot beat an equation. You can work within it. You can find clever solutions that satisfy its constraints. But the constraints remain. Gravity does not negotiate. Pressure does not compromise. The speed of light does not make exceptions for emergencies. Mars teaches us this lesson with brutal clarity. It shows us exactly what a planet looks like when a few physical parameters are just slightly different. A little less mass, a little less iron churning in the core, a little less distance from the threshold that separates a living world from a dead one. And the result is a desert so hostile that a human being, the most adaptable organism this planet has ever produced, cannot survive on its surface unprotected for even 1 minute. That, to me, is not discouraging. That is awe-inspiring. Because it means that the physics of Earth, the particular arrangement of mass and distance and chemistry and magnetic dynamics that makes this world livable, is not ordinary. It is not the default condition of rocky planets. It is something rare, something that emerged from specific physical processes operating over specific timescales, producing specific conditions that just happen to be compatible with the astonishing complexity of biological life. We are not guaranteed this. No law of physics says rocky planets must be habitable. Mars proves it. Venus proves it the other way. Too much atmosphere, too much pressure, too much heat. Earth sits in a narrow band of physical parameters, and within that band everything works. Step outside that band even a little, and you get Mars. And I think this is the real lesson. Not that Mars is impossible, but that Earth is improbable. What we have here is not the default state of matter in the universe. It is an extraordinary, unlikely, precious arrangement. A planet of the right mass, at the right distance from the right kind of star, with the right internal dynamics to maintain a magnetic field, the right atmospheric chemistry to support liquid water and moderate temperatures, the right biological history to produce an oxygen-rich atmosphere, the right geological activity to recycle carbon and regulate climate over billions of years. Change any one of those parameters significantly and you do not get Earth. You get Mars, or Venus, or something worse. And the laws of physics are the same everywhere. The same equations that govern the magnetic dynamo of Earth's core apply to Mars. Mars simply did not have the right initial conditions to sustain that dynamo. The same thermodynamics that keep our atmosphere in place govern the Martian atmosphere. Mars simply does not have enough gravity and enough magnetic protection to hold on. Physics does not play favorites. It does not care that you find Earth beautiful or that Mars looks exciting in photographs. It gives you the consequences of initial conditions, and then you deal with them. On Earth, the consequences happen to be compatible with beings like us. On Mars, they are not. So the next time somebody tells you that Mars is plan B for humanity, that if we mess up Earth, we can always move to Mars, I want you to remember the numbers. 600 pascals, minus 63 degrees, 95% carbon dioxide, 0.13% oxygen, no magnetic field, 40 times the radiation, 38% gravity, 7 months away at minimum, and a supply chain that costs tens of thousands of dollars per kilogram. There is no plan B. There is one planet in this solar system where you can walk outside naked and survive, and you are standing on it. Everything we know about physics tells us to take very, very good care of it. I would like to know what you think about that. If you had to pick the single biggest physics barrier to living on Mars, not visiting, living, which one would you choose? I am curious to hear your reasoning.